All right, guys, this is Miss Wilson again. I'm back at it with another lesson. We're at lesson number 5, Rational Roots Theorem, and we're going to begin talking about some vocabulary and key terms. So if you want to pause just to jot these notes down, be my guest, okay? If you hear any noises in the background, again, it's my 1-year-old being a 1-year-old. So go ahead, pause me, jot this down, and come back in a couple minutes. All right. All right. Welcome back. So let's look at some of our vocabulary and key terms. The first one is factors, and these are numbers or expressions that can be multiplied together. So they can be your typical factors that we're used to, like 3 times 5, and that gives us a product of 15. Or they can be factors that, when multiplied together, create a given polynomial. Now, let's look into rational numbers. Okay, so these are numbers that can be expressed as a fraction. So, for instance, a number like 0.75, well, I can represent that as a fraction of 3 over 4. Whereas a number like pi cannot necessarily be represented as a fraction. I think the closest we get, it's about 22 over 7, I believe. And 22 over 7 does not give us exactly pi. So that's what makes pi an irrational number. We cannot express it as a fraction. And that's a simplified definition, but really, these definitions of factors and rational numbers is just kind of what I want you to keep in the back of your head while we talk about the rational roots theorem. All right, so moving on to the rational roots theorem. Well, that states that if a polynomial that states that if a polynomial has a rational zero, p over q, then p is a factor of the constant term, and q is a factor of the leading coefficient term. So what I mean by that is we need to look at the factor and the leading coefficient of the polynomial. So in this case, our factors of the constant term, well, our constant term is 2. And if I wanted to list the factors of this number, then I would have positive and negative 1, and I could also have positive and negative 2. And these are the possible numbers that can be used to be multiplied together to give us 2. So negative 1 times negative 2 equals positive 2. Positive 2 times positive 1 equals positive 2. All right? If I look at the leading coefficient, that is also 2. And so my leading coefficient is also going to be positive 1, negative 1, positive 1, and negative 2. So now that I have my factors for the constant term and my factors for the leading coefficient, I can go ahead and use the rational roots theorem to find possible rational zeros. And again, when we are looking for possible rational zeros, that means that these are non-complex numbers, okay? These are numbers that could technically be represented or expressed as a fraction. And these are possible zeros, all right? Which means that these are possible solutions. So if I were to take these numbers and plug them back into the polynomial, if it was an actual zero or actual solution, then the polynomial or the polynomial will be equal 0, okay? So when you get the possible rational zeros, you technically have to check them by plugging them back in or by using synthetic division or long division to see, does this go back into the polynomial? Does the 0 go back into the polynomial? Can it be divided into the polynomial without a remainder? Sometimes you'll end up with a lot of possible zeros, and so maybe the best way might be to graph it or to use some other kind of method to check, okay? So let's go ahead and find out what some possible rational zeros are, all right? So we could have, I like to call it your P's and Q's, okay? And so what you're technically doing is you're taking the factors and from the constant term, and you're taking the factors from the leading coefficient term, and you're basically making fractions out of them. And based off of these fractions, these are going to be your P's over Q's. These are going to be your possible rational zeros, okay? So if I were to make a whole bunch of fractions based off of these two factors, I would have positive and negative 1. I would have positive negative 2. But then I would also have positive and negative 1 over 2, okay? So let's think about it like this. I could take this negative 1 here and put that over this negative 1 here, and that would give me positive 1. I could take this negative 1 and put it over this positive 1, and I would get negative 1. I could take this 2 over this negative 1, get negative 2. I could take this 2 over positive 1 and get positive 2. I could take this 1, positive 1, and put it over this positive 2 and get positive 1/2. I could take this negative 1 over positive 2 and get negative 1/2. So all of these different combinations of positive 1, negative 1, positive 1, positive 2, and negative 2 would make these possible rational zeros, okay? So really, for this particular question, it just really wants to know what are your possible rational zeros. And so all I'm going to go ahead and do is just rewrite my answers from part 3, which is positive and negative 1, positive and negative 2, positive and negative 1/2, okay? For this particular problem, we are not stopping to check to see if these actual zeros exist for this polynomial because we're not going to plug them back in, all right? All right, so let's go ahead and move on to the next page. Okay, guys, so now we're going to move on to example number 2. And I need you guys to make a quick change on your paper for me. I realized there's a typo for the polynomial g of x. Instead of then our constant term being 12, it should actually just be negative 2. So I want you to go ahead and cross out that g of x, and we're going to rewrite it. And instead, you're going to put 3x to the power of 4 minus 4x to the power of 3 plus 3x minus 2, all right? And this will also make your life a whole lot easier if you do it this way. All right, so let's start with listing our factors of the constant term. So in this case, our constant term is negative 2. So my possible factors for negative 2 include negative 1 and positive 1. It includes positive 2 and negative 2. All right. Now I'm going to look at my leading coefficient, which is positive 3, and some possible not possible, but the factors of positive 3 are positive 1, negative 1, positive 3, and negative 3, okay? And now I'm going to use my rational roots theorem, which is my P's and Q's, to go ahead and identify possible rational zeros. So possible rational zeros would include positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 1/2, positive and negative 1/3. All right? So what we're going to do is, so now we have a step 4 here. And so what we're going to do is we're going to take one of these possible rational roots, and we're going to go ahead and try to plug them in back into the equation just to see if it's a possible zero, okay? So there are multiple ways that you can do this. Ways that you can check You can use long division. You can use synthetic division. You can also plug in for 0 or plug in for x, which means substitute. And in some cases, if you have the technology, you can graph it. All right, so these are possible ways that you can check to see if it's an actual 0. All right, so I know what one of the zeros are for this particular polynomial. So what I'm going to have us do is I'm going to go ahead and we're going to check two different ones. We're going to check ones that I know isn't a 0, and we're going to check one that we know is a 0. Okay, so let's start with -1, and we're going to also try +1. All right, so let's try with synthetic division. All right, so I'm going to start with -1, and I'm going to do some synthetic division. So I'm going to have a 3 with a -4 here. I need to put a placeholder in for x squared. I'm going to have a +3 and a -2. I'm going to start by bringing down that 3. So -1 times -3 is -3. -4 plus -3 is -7. -1 times -7 is +7. 0 plus 7 is 7. -1 times 7 is -7. 3 plus -7 is -4. -1 times -4 is +4. And then -2 plus +4 is +2. So if I went ahead and checked this, this would give me 3x cubed minus 7x squared plus 7x minus 4 with the remainder of 2 over x plus 1. Okay, and so since I have a remainder, I know that -1 is not a 0. Okay, so I went ahead and checked that one. -1 is not a 0. Well, let me go ahead and try out +1. So I'm going to now do the synthetic division again, but this time I'm going to do it with +1. So I'm going to have 3, -4, 0, 3, -2. I'm going to bring down my 3. 1 times 3 is 3. -4 plus 3 is is -1. -1 times -1 is, 1 times -1 is -1. 0 plus -1 is -1. 1 times -1 is -1. 3 plus -1 is 2. 1 times 2 is 2. -2 plus 2 is 0. I have no remainder. So since I have no remainder, that means that 1 is a 0 of g of x. Okay? All right, so that's basically the gist of the rational roots theorem. You have to identify the factors of the constant term. You then identify the factors of the leading coefficient. You use the rational roots theorem to find possible zeros by listing your p over q's. And then you can use long division, synthetic division, plug in for a substitute, like you could substitute for x, or you can graph it if you have the technology with you to be able to determine what are the actual zeros once you've received the possible rational zeros from using the rational roots theorem. Okay? All right, so go ahead and sum up your notes at the bottom, and feel free to ask me or Mr. Klawan any questions you may have about this theorem. All right, bye-bye.